Everyone. My name is Chaima Hkimi. I'm a bioinformatics PhD candidate at Institut Pasteur of Tunis. I'm affiliated to the Laboratory of Bioinformatics, Biomathematics, and Biostatistics, which is for BIMS. And today I'm going to present you my talk titled Leveraging Artificial Intelligence for Predicting Human Viral Protein-Protein Interactions, a benchmarking study to address key challenges. So, as you know, viral infections have significantly contributed to the global burden of disease, as evidenced in the last decades with multiple viral pandemics and outbreaks. And to understand this kind of viral infections, it is imperative to understand the human viral interactions that are also mediated by PPIs, as they determine the cause of infection, the host immune response, the outcome of disease, and ultimately to identify targets for therapeutic interventions. So while many experimental and traditional methods has contributed to identifying and analyzing these kind of interactions, they still time-consuming and cost ineffective and labor-intensive, especially for endemic countries. So here what it comes the alternative as the computational approaches, as homology-based or structure-based, domain and motif-based interaction approaches, and more recently we're talking about AI-driven approaches such as traditional machine learning or deep learning for their ability to handle complex data sets and to uncover more intricate interaction patterns. So despite the growing use of these kind of traditional ML models for predicting these HV PPIs, there's no systematic and comprehensive study that will evaluate and compare these kind of performance across diverse systems. So that's why in our study, we designed a protocol that would benchmark various ML models and to comprehensively assess the performance from three key aspects. So the application of a different feature representation to a protein sequence, the effectiveness of the different ML classification across various ratios for the balanced and imbalanced, and for a diverse data sets that we chose to work with these kind of species. And that's to provide some valuable insights and recommendation when it comes to building these kind of ML models to predicting these kind of interactions. And also we ended up with a little bit of biological insight to apply somehow the best performing model to analyze the human SARS-CoV PPI network as a case study, and we proposed some kind of hypotheses that would maybe contribute to the identification of a new antiviral targets. So when it comes to our applied methods, because we gather the experimentally verified HV PPIs for our positive data set from these various resources. And then we chose to work with the West Nile and HIV and SARS-CoV-2 because of their health impact, and plus the availability of the related data, and they are different data sets you can see here. So because we are using a sequence-based approach, so we have to extract the protein sequences for the human and for the aforementioned viruses, and then we process them, and we ended up with these kind of data sets. So somehow we have a really small data set, like a middle data set, and much bigger data set. Now, when it comes to our negative data sets, unfortunately, there's no standard protocol or strategies to get such kind of data sets. So what we use is the traditional way, is to randomly select the pairs of protein pairs from a pool of unknown interactions. And how we did that, we extracted the complete proteomes for the Homo sapiens as the selected viruses, and then we paired all the human and the viruses proteins to create all possible interactions. Then we removed what we already selected for the positive interactions, and we considered what remains as our negative data set. So here, after collecting and creating the positive and negative interactions, we created our different data set based on our different ratios. R1 is for the balanced data set, and the R25, 15, and 100 for our balanced data set for ratio 125, 150, and 100. And then we created our dependent data set to evaluate our model, and we selected randomly 1/5 of the negative and 1/5 of the positive data sets. And what remains, we let it as a training data set, and we chose to work with a 5-fold cross-validation, and we worked with the grid search CV to select the best parameters for our models. And then here we chose to work with these kind of descriptors. They are the most known and commonly used once, and then we created a combination set to combine all the different descriptors, and these kind of descriptors all have the ability to adapt to the protein sequences no matter what the length is. And then we used also the commonly used machine learning models for these kinds of studies, and also the evaluation metrics that everyone works with. So when it comes to the results, here we are looking to compare the performance and evaluation based on the accuracy. So here the red one is for the West Nile, the green one is for the HIV, and the blue one is for the SARS-CoV-2. And then you can see here, we see a notable rise in the accuracy as the class imbalance increase, but somehow this is a misleading improvement because it's really highlighting the model bias towards predicting the negative interactions, which we don't like to see that because we are trying to predict the positive interactions, not the negative ones. And you can see that by the F1 score. So as the imbalance increases, also the F1 scores has a tendency to decrease. So our model is really trying to pick the negative interactions more than positive interactions. So when it comes to choosing somehow the ratio for this kind of studies, we really prioritize to use the 1:1 ratio to ensure a more balanced learning and enhance the sensitivity. But unfortunately, if we are going to talk about the real world data sets, we are really in the imbalanced issue. So somehow we would address this issue by using the SMOT technique that it will help us to get the issue of the imbalancing, because we are really trying to generate a synthetic examples more than duplicating the data. Now, if we're going to look for how the features based on the top models, how it's working with our different data set, and this is only for the 1:1 ratios, we see here that we have a problem with the West Nile dataset because it's too small, and we do have an overfitting issues and memorizing issues somehow with the DPC and QSO. But as you can see for the CTIP-SC, we can see that we do have a beautiful accuracies, but for me, I would not recommend to use this kind of a model to build an application because it's really small. And if we're gonna give it for an application and we're gonna give it more bigger data set, things are gonna shift. It's not gonna stay the same. So as a recommendation, somehow we are here using the supervised machine learning, and for this kind of studies, we are really relying on expert level data, especially for the positive data set. So somehow we can overcome this limitation is we can consider to overcome it by using semi-supervised or unsupervised learning also. Now, when we come to more complex and bigger data sets for the HIV-1, we do have see the accuracies here has a drop for the CT, PIC, QSO, but still we have some consistency with the different metrics. But somehow with the DPC and combination set for the GBM, which is the best model, we see an overfitting issues. Also with the SARS-CoV-2, we are seeing the GBM is overfitting for all the features. And this kind of a problem here for the GBM, generally it is a robust for this kind of overfitting issues, but sometimes when the model becomes more complex with the more features, it has this issue, we'll start to be seeing these issues. And for this several best practices that we can apply, we can limit the depth of the trees, so we can prevent the model from becoming overly complex. We can use also the early stopping, so to prevent the excessive iteration. And also we have to consider careful hyperparameter tuning, because in our study, we didn't did the hyperparameter tuning because we're trying to compare the models as it is. So for the case study for the SARS-CoV, we used, I'm just going to go back here. We used the most efficient one is the SVM model because somehow it showed the best performance. And here we are seeing we are successfully identified and predicted 333 protein-protein interactions involving 321 human proteins with a 17 SARS-CoV proteins. And we can see here we compared what we found with the 3 different data sets and 3 different studies, and we had a 75 uniquely overlapped PPIs. And now when it comes to when it comes to identifying or analyzing our network, we did identify several human proteins that might be interacting with the SARS-CoV-S protein, and one of them is the TLR4, which is known for its associated, which is recognized in the pumps and it's going to result to sensitizing various inflammatory cytokines. And this possibility of a direct interaction with S protein with the TLR4 is to mediate the antiviral immunity, especially when it has been previously identified as a key target to develop inhibitors and immunotherapeutic strategies. So another possibility of interaction is TRIM7 to be interacted with an SNP12 and SNP7. And the TRIM7 is an E3 ubiquitin protein ligase known as an interstic antiviral. And we also know that the TRIM7, and it was been experimentally verified, that it has an ability to interact with the SNP8 and SNP5 via the glutamine and motif binding mechanism. And this latter is also shared by the NSP12 and NSP7, which could have the possibility of this interaction maybe happening, and also that would lead to the ubiquitation and proteasomal degradation. That's the possibility to the replication of SARS-CoV-2 replication. And I'm going to end up with this also possibility of interaction between the ACTM4 and ORF6. ACTM4 has, it is a host factor of actinin-4, which was originally known for its capacity to bind into NSNP12. And when it's binding to NSNP12, there's a suppression of replication for the SARS-CoV-2. And we know that ORF6 is the most toxic protein for SARS-CoV-2, and when it's overly expressed, has the ability to restore this kind of replication. So our theory is, or hypothesis though, is when ACTM4 is binding to the NSP12, we have a stop of replication. And this, when ORF6 has the ability to bind to ACTN4, we can restore this kind of replication. So as a final take-home message, building an effective machine learning models for this kind of task, it was require careful consideration for several factors, such as the dataset composition, the feature representation, also how the model is, the complexity of the model. And while some models demonstrated somehow a promising predictive capabilities, others had shown other issues like the memorizing and overfitting issues. And as a future work, we should focus more on improving these kind of models, and maybe go to explore more alternative representation techniques and other models also, or ML, or maybe deep learning also. So finally, I really want to thank my supervisor, Dr. Kaiser Dira, and also my team for their constant support. Also, I want to thank the African Bioinformatics Institute for providing me with a travel fellowship to be here with you guys. And thank you for listening.
Thank you, Chaima, for your presentation. I think I will ask one question. And then we'll move on to the last speaker. So I just wanted to find out the possibility of including structural information in your predictions. Is that going to be considered in future, depending if there's structural data available?
Because we use the sequencer proteins, I know when we're working with proteins, we have to work with more structure because we have more information. But the thing is, I wanted to include the structural descriptors for that too. But the problem with the structured descriptors that they call for third-party algorithms, and those third-party algorithms will be losing information at some point because we don't have a lot of information about all the proteins. So I really wanted to take, because we still have a little bit of a positive interactions, and if we're gonna lose more information, our model will be dropping in accuracy more and more. So yeah.